Hello, everyone. We are live now. Thank you for joining us. It's very exciting to be back for the second, opening of the Learning Salon. I realize now that there's another session and some people were there. And when I went live, I could bring them over. So while John does our intro into the sort of the new series and the new format, which would be bi-weekly, I will just post a link there, and I can see that about 20 or 30 people just joined from the other session. So I'm just going to add the link there too. John, please take it away.
Yeah, so hi everyone. I know it was quite a lengthy hiatus, but I want everyone to know that the Salon is more than a COVID phenomenon. I think it was successful enough to deserve another season. For those of you who didn't see it, there was actually quite a nice article that Neuron asked us to write about the Learning Salon and its ethos. I think that's actually open to anyone who goes to the Neuron website, so you can get a sense of what we were trying to do. I actually think the article came out very nicely. Ida was the lead author of that, so please read it. The format's going to be a little bit different. Jovo is taking somewhat of a sabbatical, and so he'll be more of a guest host with us. We're also going to try something new, if I understand it rightly, Ida, which is we'll have guest hosts come in sometimes. We've had that in a way almost de facto, for example, with Melanie Mitchell. She was all but our fourth member. So we're going to keep on experimenting in the spirit of the Salon anyway. We're also going to be bi-weekly for the time being, just so people can get a bit of a breather. And it's just, not that easy to get 52 slots a year with people that want to be on, or we want to have on, let's be honest. So that's that. We're very, very excited to have Grace on. I think it's a wonderful way to open the second season, start really strong. I think Ida will introduce Grace, and then if you remember the format, the speaker gives about a 15-minute, 20-minute talk, and then it's open to discussion. The way that works is, Ida and I will give Grace a hard time, and then people come in from the chat or other sources. Again, remember what the spirit of this is. It's to really have a deep discussion, to ask questions where one is genuinely puzzled. This is not an opportunity to show off or play clever. We want everyone to feel comfortable and really go at it. I think this particular day is a great way to show that, because the book is such a thoughtful piece and covers so many important topics. I think it's almost perfect for something like the Salon. So I think it can bring out all the best behavior and the best type of questions. And I think we'll go from there and let Ida introduce Grace, and then we'll go to the talk, and then we'll discuss the book.
Thank you so much, John. Yeah, it's quite fantastic to discuss Grace's book. When I invited her and she was willing to take the first date, I was very happy about that. I personally really enjoyed the book, Grace. So for everyone who doesn't know Grace, who's not on Twitter perhaps, Grace is a computational neuroscientist. She finished her PhD right here in New York City at the Theoretical Neuroscience Center at Columbia University with Kim Miller. And currently, she's a Sainsbury Wellcome Center and Gatsby Computational Neuroscience Unit postdoc or research fellow, sorry. She works on building functional and interpretable models for sensory processing. As someone who works on models and neuroscience of memory, learning, planning, higher cognition, I think there is a very nice sort of complementary overlap between the sensory history and the learning / memory / planning history of computational models in neuroscience. And I really appreciated the way that I think the way Grace talked about sensory models kind of anticipated this link to other modes of cognition in her book. I think that it was a very kind of general book. I personally really enjoyed even the simplicity and the way that the sentences were phrased or some examples were used. I was very positively, honestly surprised, because usually science books are not as exciting for us who are in the field. And this one was actually super well written. I'm very curious to see what Grace would like to say about it. Usually when I introduce the book, I show the book, but in this case, I'm going to show my Kindle, because in this case, I read the book here. Yeah, I would love to hear about it. As always, please remember to be respectful of one another. When you're making comments, we will be monitoring the chats for written questions. Ask your questions in the Ask a Question button that is exactly below. And just make sure to vote on each other's questions every now and then. We will answer the clarification questions in the chat, and afterwards we will sort of bring some folks on screen. If you don't want to be brought on screen, next to your question in the Ask a Question area, say ask for me, so we don't invite you and we don't lose time over that. Fun fact about Grace, she just put her baby to sleep before joining our session, so we're very much hoping that the baby keeps napping during this time. And take it away, Grace. We're excited. Please share your screen, and would love to hear about your talk. And while you're setting up, if anyone can put the wrong link where you were at first, because I pulled some people from another place when I was going live. If you can put the wrong link so I can find there and tell people that this is the correct link. Thank you so much.
Okay. Am I sharing correctly? Double checking.
Yes, perfect.
Okay, cool. So yeah, thank you so much for the invitation to join the Learning Salon today, and glad to hear that you guys have been enjoying the book. So I guess I wanted to start by giving kind of an overview of the book and the motivation really for writing this book. So the book is called Models of the Mind, and the subtitle is How Physics, Engineering, and Mathematics Have Shaped Our Understanding of the Brain. And so really what it is kind of an overview of the field of computational neuroscience, or, an overview of mathematical approaches to understanding the brain. And part of why I wanted to write the book was just because in my experience, being in this field and talking to people outside of it, people don't know what it is. If you tell someone that you're a computational neuroscientist, they don't have any follow-up questions. They don't have any point of reference for what that means. Yet at the same time, I feel like the computational side of neuroscience and the modeling side of neuroscience is just becoming more and more popular and important within the field of neuroscience, and more important for how we're understanding the brain. And so I didn't think it was fair that there's kind of, there's a good amount of popular science out there about the brain. People are interested in how the brain works and they want to read books about it. But usually those books are, either very focused on like human fMRI studies, or they're focused on neurotransmitters and talking about chemical imbalances or that kind of thing. There's just certain ways that people are used to seeing the study of the brain represented in popular science. And I wanted there to be a book that represented the mathematical side to how we study the brain. And I wanted the book to be, it's not about like any of my pet theories of how the brain works. It's not about even really methods that I prefer versus ones I don't prefer. I tried to make it an honest, like taking a step back, honestly looking at all the different areas where neuroscience has come in contact with some more quantitative field, and the very interesting things I think that have happened, when those interactions occur, and how they've shaped neuroscience and how they've shaped the other fields as well, because sometimes that influence can go both ways. So that was one of the motivations to share it with a wider audience. But I also, and this side of it kind of grew more and more as I was researching and writing the book, I wanted to share the history of the field with people in the field, because there isn't really a kind of compilation of the stories of computational neuroscience. There isn't a book that kind of talks about the history of this field. And so I wanted to compile that to share it with scientists in the field, because as I was doing this research, I was realizing how kind of fruitful it was for me to know more about the history, and to see the stories and kind of the human side as well of how the science got done, and how many things were a result of, luck or happenstance or whatever. And just, seeing how these interactions took place in the past, kind of contextualizes what you're doing in the present as a working scientist. And so, I wanted it to be, a fun way for people to learn about that history as well, even if they kind of already know about the topic matter. I think a lot of scientists, I'm assuming because I didn't know most of the stuff that's in the book, I think a lot of scientists will find things that they don't know, even if they've been in the field for a while. But so computational neuroscience is a very, very diverse field. It's basically like any time that mathematics and something about the brain have come in contact. So the book is organized in separate chapters that are almost like standalone narrative essays about different topics. And they start with kind of small scale, so single neuron models, and then going up to models of populations of neurons and how they interact, through to kind of modeling even at the behavioral level, mathematical models to capture behavior and how those can relate to neural processing. So it's meant to really cover, as I said, kind of a broad range of what computational neuroscience is, and not putting forth any specific theory or really like trying to make any specific argument, except for the fact that this combination of studying the brain using mathematics is like really interesting and fruitful and exciting. So I think that's the main argument of the book. So for this talk, I was going to just tell kind of a few short stories from the book, so you get a sense of the history side of it, which I think is good to know, as I said. And specifically, I'm focusing on these two chapters, chapter 3, which is called Learning to Compute, and chapter 6, which is Stages of Sight. And these both talk about artificial neural networks to some extent. And so that's what I'm going to focus on, because that seemed like a good point of interaction for this group, this intersection of neuroscience and AI in the form of artificial neural networks. And it gives you a sense of kind of what I'm talking about when I say I'm telling the history of these stories, at least, in the first part of the chapter before it goes on to what's happening in the modern day. So, so I'm just going to start off with chapter 3. So the history of artificial neural networks starts partly with this man, Walter Pitts, who was doing work that's very relevant here in the 1940s. But before that, he was a teenager in Detroit, and he had a very rough childhood. There's stories of him escaping to the library to hide from the other kids that were picking on him. And but when he was in there and when he was at home, he would really like devour advanced text. He was just clearly naturally very smart from a young age, even though he wasn't in an environment that could really nurture that. But he had all of these interests that he pursued on his own, to the extent of even running away from his family when he was 14, to go to the University of Chicago. Not to actually go to the University of Chicago as a student, but to just hang out around the University of Chicago, because he heard that Bertrand Russell was going to be a visiting lecturer there. And he had read Bertrand Russell's Principia Mathematica, and was interested in logic and mathematics and the philosophy of those things. And so he went to just kind of sneak into these lectures and classes, and just hung around for a while, even after Bertrand Russell left. And he just kind of made friends with researchers there, philosophers, mathematicians, people who were working at the intersection of biology and mathematics, which was somewhat new field at the time. So he never finished high school. He never formally enrolled as a graduate student, but he was doing research basically for these people, because he was around and he was interested and he was talented. Warren Mcculloch, his kind of route to doing this kind of research is far more traditional. He was trained as a physician, and he also studied philosophy. And so he had these, joint interests of, knowledge about the brain as a physical object, but also a lot of questions were swirling in his head about philosophy of mind and how we think of, what the mind does and where does thought come from, and how do you relate the physical object of the brain with what we call the mind and thought. And he was a big fan of Leibniz and his philosophy on the mind. And really, in a way, having this intersection of interests was unique for the time, because people weren't really trying to understand how the brain led to the mind. It was a time where those things were studied more separately and kind of acceptably separate. You had psychoanalysis for the mind, and you had physiology for neurons and other cells in the body, but there wasn't a pressing sense that you needed to connect those things. It just didn't seem like that was of interest at the time. His interest in both of those did make him unique and a bit eccentric, kind of, willing to go out on a limb and not be the traditional physician like he was trained. So he was at, Mcculloch was at the University of Illinois, Chicago as a professor. And so at some point, he and Pitts met. There's actually a few conflicting stories of how they met. But clearly they had overlapping interests. They were in the same city. Eventually they were at the same meeting or someone put them in contact and they started talking. And from Mcculloch's perspective, he had these kind of vague ideas about how neurons could be doing the computations necessary for thought, but he didn't have analytical training. As I said, he was kind of a philosopher and physician. But Pitts, as I said, was very analytical. And so when they met, it was kind of this sense of, oh, like this is the person who can, they can complete each other's ideas in a way. And so they started working together. And not only that, Pitts actually moved in with Warren Mcculloch and his wife because, as I said, he had run away from home and was basically homeless in Chicago. And so they really formed a tight bond and a relationship, both a working relationship as well as a friendship, because they had all of these overlapping interests in philosophy, and they wanted to work on this model of how neurons can work to create the mind. So the results of all of that collaboration was this 1943 paper, A Logical Calculus of the Ideas Eminent in Nervous Activity. And I'm showing here the first 3 pages of the paper, just because if you skim through this, you can see kind of how rooted they were in physiology. They just start the paper just by kind of listing almost all of the known facts about the physiology of a neuron at the time. They're talking about synapses and axons and conduction delays and the all or none principle and inhibitory versus excitatory connections and all of these things. They're just really rooted in the physiology. That's where they're coming from. This wasn't an abstract exercise, really. I mean, it feels abstract, this idea of turning neurons into computational devices, but it was really, they were well versed, in the physical nature of the brain, at least what was known about it at the time. And so starting from those kind of that rich understanding of the physiology, they did have to boil down what they thought were, kind of the most relevant pieces of how neurons work to be able to use them as a model. And so they focus on, you can kind of see it at the bottom of the last page there, there's a few assumptions that they go into their calculations with. And so part of it is the idea that a neuron is all or none, so it's either firing or not firing. It doesn't have graded outputs. You need a certain amount of inputs to make a neuron fire. In their case, they treat an inhibitory synapse as absolute. So if a cell is getting an inhibitory input, it can't fire no matter what else is happening. And they're also assuming that their networks don't change over time. So they're kind of defining connectivity between neurons and studying this fixed connectivity. And the really, amazing thing that they were able to do once they boiled the physiology of neurons down to these kind of basic, this basic essence of what a neuron is and what it does, is that they were able to show that you can connect neurons in such a way that they can implement logical functions. So if you think of a neuron as representing a statement and its activity as representing the truth value of that statement, so truth values means the statement can be true or false. And the same way, a neuron, because it has this all or none principle, can be on or off. It's active or not active. So there's that mapping there. The binary response of a neuron can be mapped to a binary truth value. And so if you wanted to then connect neurons in a way that implements the logical operator and, that's shown here in this these diagrams, which was published in Mcculloch and Pitt's paper. So C here is and how this works is that if the first neuron is on and the second neuron is on, then the third neuron here will be receiving 2 inputs, and they design these neurons such that the neuron needs 2 or more inputs to fire. That's the threshold of the neuron. And so that means that neuron 1 and neuron 2 need to be on for neuron 3 to be on. So that's implementing and. In order to implement or, you can, again, have a third neuron that requires 2 inputs to be on, but in this case, each of the input neurons sends a connection of strength 2. So now you can have neuron 1 on or neuron 2 on, and neuron 3 will be on as a result. And so you can see here, they just kind of built up more and more complex circuits that could implement more and more complex logical statements. And they use inhibitory neurons for the negation. And they really just show, once you start with the basics, the way logic works is you can just keep building up and up and up. And you can do the same thing with the neural circuits. So this connection between the physical nature of what neurons do and logic obviously opens up a lot of doors because it means anything that you can do with logic, you can do with the brain, basically. And that's a huge leap. That's, as I said, a leap that people weren't even looking to make really at the time. And a colleague of Mcculloch and Pitt's went so far as to say that their work killed dualism. So killed this kind of notion that the mind is separate from the body. You can now explain the mind with facts about the body. Perhaps even more influential than killing dualism, Mcculloch and Pitt's work influenced John von Neumann in his design of the modern computer architecture. He saw their binary neurons and thought about those connections and how that works when he was thinking about computing. And this was through these Macy Foundation lectures that were explicitly meant to bring people together who had an interest in taking biological inspiration for building machines. So that was a very fruitful multidisciplinary conference that really represents this kind of synergy that can happen when biology and mathematics meet. Actual neuroscientists at the time, though, did not take much from Mcculloch and Pitt's paper, which again could be relatable to some things today where there can be a divide between experimentalists and theorists, and sometimes they don't communicate well with each other. So the paper was described as not for the lay reader, which is probably true because after all their physiology, they get into some very specific notation for their models. And people were saying that, physiologists would obviously need to become more familiar with mathematics for this kind of work to be useful for them, or the mathematicians need to explain their conclusions in an easier way for the physiologists to understand. So it didn't, the artificial neural networks of Mcculloch and Pitts didn't actually impact neuroscience so much at the time. Now we know today that artificial neural networks are used a lot in neuroscience and have been used a lot in neuroscience in the past. And people do kind of accept them as models and understand how they work. And so I just want to kind of get into a little bit of that transition, particularly for convolutional neural networks, which are used as models of the visual system. So the first thing to realize is that the artificial neural network that is popular today, while its basic concepts are rooted in Mcculloch and Pitts, the idea of thinking of a neuron as this kind of simple input-output function, and that fact that can lead you to a lot of computational power, that's still the core of it. But the exact form of the artificial neuron that we use today is based more on what Frank Rosenblatt did for the perceptron. So the important thing that's different about this kind of neuron is that it's not based on implementing logical functions. You don't have to create a circuit that has this precise connectivity, and you don't have to be able to map what the neuron is doing to a logical statement. In the perceptron, you have this nonlinear input-output function. You have this neural unit, but the weights that go into the neuron are learned, so they're not mapped to anything in particular. They're just whatever works. And the output also doesn't even have to be binary. You can have a continuous value output for your neuron. So it really breaks the connection to formal logic, which is what was so kind of beautiful about what Mcculloch and Pitts did. But it turns out that that's not necessary and not going to be the most fruitful way to utilize neural-like units in artificial intelligence. So we're dealing with a different type of artificial neuron now. Speaking specifically about convolutional neural networks and where they come from, we have to again go back to the physiology, because they have a design that's directly inspired by the experiments that were done by Hubel and Wiesel in the 1960s. And so these were experiments with cats, where cats were shown images on a screen, and they were recording from the visual cortex in the cats. And it was already known that cells in the visual system tend to have spatial receptive fields, so areas in space that the neuron responds to. That if it's going to have something, it has to be in a specific area of space for that neuron to respond to it. But then they were trying to figure out, kind of aside from the specific area in space, what kind of other features did there need to be to get a cell in primary visual cortex to respond? And on accident, they discovered that cells in the primary visual cortex respond strongly to oriented bars of light, which you can see in this diagram here. And so different cells have different preferred orientations that they respond strongest to, and they lower their response as you deviate from that preferred orientation. And so those kinds of cells that have a very precise spatial location and then also a preferred orientation, those were called simple cells by Hubel and Wiesel. They also discovered complex cells, which were cells that also had a preferred orientation, but were a little more forgiving in where exactly in space that oriented line had to be. And so those were called complex cells. And again, kind of what Hubel and Wiesel discovered here is a kind of a logic to the circuit architecture. They realized that to get the response of a simple cell, what you could do is kind of pool the responses of the inputs to the visual cortex, which come from LGN, and those neurons respond to points of light, not to bars. But if you put points in a row, you get a bar, you get a line. So they realized that simple cells must be getting a very specific alignment of inputs from the LGN, and the complex cells could have their response if they got a specific set of inputs from the simple cells. So they get simple cells that all have the same preferred orientation, but have slightly different preferred spatial locations. And now you can have a complex cell. And so they were really able to kind of reverse engineer the logic of the primary visual cortex. Now, a little while after they published those papers, Kunihiko Fukushima, who was an engineer at the Japanese National Broadcasting Corporation, he heard about the work of Hubel and Wiesel because at this broadcasting company, they had teams of psychologists and physiologists who were also working there, which is, a point of explicit interdisciplinary interaction. They would have these different teams that were familiar with their own literature, and they would have them meet regularly to share findings from each other's fields. And so as an engineer, he heard about Hubel and Wiesel and thought, oh, I can use those basic principles to develop an artificial visual system. And so that's what he did. And you can see the design of it here. This is a version of it called the neocognitron. And also in his paper, you see he has this kind of simple diagram of what the visual cortex in cats, as it was studied, are doing. And he even uses the terminology of calling his layers S and C for simple and complex cells. Now you can also see on the top here that he had this ordering of, the simple cells lead into the complex cells. There were also some findings about kind of these hyper-complex cells that had more specific response properties. But then after that, there's this question mark. Because in an interview later, he explains he expected Hubel and Wiesel to keep going in their studies, to go to the next visual area and figure out the logic there and keep going so that you could find out the response properties along the whole pathway. But that's not the direction that their research went. And so he had to decide what to do with his model. And he decided to just kind of keep stacking simple and complex cells. So you'd have this model where you have an input image, you have a layer of artificial neurons that get input from that input image, and they're looking for simple features like oriented lines. Then you have another layer of artificial neurons that are getting input from the first layer, and they're taking a collection of input from these simple cells that all have the same preferred feature, but different spatial locations, and they're creating these complex cells. And then you just take simple cells who start to look for patterns in the complex cells, and you repeat and you repeat and you repeat. And so this alternating of simple and complex layers is what we see in modern convolutional neural networks. It's just called convolutional layers and pooling layers now. And then you kind of concatenate all of those layers and stack them up to get a model that can kind of complete the full transformation that's done in the primate visual cortex or in the biological visual system. So that architecture, the broad architecture is taken from the physiology of the visual system. The microarchitecture of using these artificial neurons is taken from the even older physiology of individual neurons that Mcculloch and Pitts used to inspire their model. So that gives you a sense of kind of some of the history that's covered and kind of, what I was saying about finding these interesting tidbits in the history where there really was kind of an explicit point where there was the ability for people on the quantitative side and people on the neuroscience or biology side to interact, and then really seeing what grows from that and how interesting it can be. So thanks. I'm looking forward to any discussion that comes from this or the rest of the book.
Thank you very much.
Thank you so much.
Superb. Yeah.
This was such a fantastic exploration of those two chapters. I want to remind everyone that they can leave their questions in the Ask a Question area or in the chat area. Although this was a little different than usual, that it was a little bit more on the history side than on the proposal side. But I would love to open the screen to John to start asking any questions first. And I'll monitor the chat. So anybody who has comments they want to have in the chat, please.
Can you hear me, Grace? Yeah, okay. Well, first of all, I want to say, and this is deadly serious, just everyone who's in neuroscience, whether you're a layperson interested in it or a neuroscientist, you should read this book. And I don't say that lightly. And I just think it's very special. And I think there are a number of reasons for that. One is that it really does bring to the fore the importance of actual books and essays for thinking about subjects. Two, I really do think that the history that Grace really covers really well is not just a spicy topping. It's actually really important to have a sense of how the ideas traced out. Also, when you give a history of ideas, it actually is at the same time an act of synthesis, right? Because you can see, just like in the talk that Grace gave, where these things cross-pollinated. I also think that it's very well written. I think the analogies are really good. I think it's witty. I think the footnotes are very well chosen and fascinating. I just can't praise it enough in terms of what it does. And then underneath it is a position. It's not just a set of essays. There's an argument, beginning to be constructed. And I want to talk about some of those. So I really do think that that anyone who wants to sort of see what they're missing in terms of when they read just papers, this is the way that a book should be written and constructed. I'm both in awe and envious.
This is a lot nicer than I'm expecting the Learning Salon experience to be.
Well, no, because we're not here to be critical for the sake of being critical. I think praise should be. And also, finally, I'll say, you're finishing a postdoc, and to do something like this takes maturity. And, it's just a very mature book for somebody, if I may say, is early and young in their career. It's not easy to pull this kind of thing off. It's sort of amazing. So really what I'd like to do is, just sort of take that synthetic overview that you have and sort of have a talk about what you think is going on in neuroscience, and maybe look at some of the subtexts that I saw in your book. Some may be very explicit with respect to what you had in mind versus some stuff which might be implicit. Right. Mm-hmm. So, I'd sort of like to start with, and I've noticed this happen, and I would like your position, is you call it models of the mind. So the mind is a complicated term. You didn't say models of the brain, and I can sort of see why in a way. It's nice to have the M and the M, right? Yeah. And then, Sean Carroll, who I actually had the luck to go and have dinner with about a month ago here in Baltimore, when he says, this will change the way you think about thinking. Now, what I'd kind of argue is that this is an amazing biopsy of the current state of neuroscience through the lens of computation. And one thing, I'm sure you're aware, there are some sort of historians of science, when they think about the scientific revolution and science in general. For example, there's this philosopher and historian of science, David Wooten, who actually writes, I found the quote for you, that the scientific revolution was first and foremost a revolt by the mathematicians against the authority of the philosophers, right? And then there are other people who say that when a science has matured, when you can begin to formalize it mathematically. And you actually have a quote in your book on page 312 when you say, I think along these lines, when any field of science amasses enough quantitative data, it eventually turns to mathematical modeling to make sense of it. So in other words, it's almost as though you're saying that in a way, facts become knowledge when they can be formalized in some way. And probably the best way to turn facts into knowledge in science is mathematical. So would you say that you adhere to that view that as a science matures, as it goes from data collection and anecdote and verbalization, that its mathematicalization and formalizing is just what one would expect as a field matures? Would that be fair to say that that's kind of your position?
Yeah, I could see how you would get that from it, but I don't know if that's exactly how I feel about it. I think I kind of lay out in the first chapter of the book why I feel like the brain is particularly well suited to be studied with mathematical methods. And, it's just about having this object that's so incredibly complicated that you can't get very far if you don't start writing things down precisely. And there's, it's recurrent and nonlinear, and there's just, your intuitions are intuitions that are based in a much kind of simpler view of the world, are going to break down very quickly when we try to understand very complex things with a lot of interactions. And so that's part of the reason why very quickly in neuroscience, I feel like you need to start defining things in terms of mathematical models. There was a paper that I read when I was doing research for the book, and I wish I could remember what it was now, but it talked about this idea that actually psychology may have quantified itself too early and became kind of mathematical before it was ready to be. And it was just this idea that you could quantify things that you were studying in the lab, and you could give them formal names and define mathematical relations between them, but the actual kind of base intuitions and the kind of way that you're parsing up the concepts and choosing to quantify them, maybe psychology wasn't ready for that by the time that it started quantifying things. And so I don't think that building a mathematical model is necessarily better than not having one. I think it's you have to consider what's appropriate for the question and what's appropriate for the level and precision of the data that you have. If you prematurely quantify, then you're just kind of codifying what was maybe popular at the time, but you're not building a robust framework for incorporating future evidence potentially.
Yes, yeah. I mean, I wasn't in any way trying to impose a single view. I just think it's very interesting how your book, as it unfolds, from single neurons all the way to sort of inference and decision making, we'll get to that in a minute, can show varying degrees of formalization. Although it is nice that you do choose along the spectrum all those components that can be subjected to a more mathematical treatment. So getting back to the mind thing, when you look very carefully at your book, whether it's, action potential, perception, sound localization, motor cortex, you have a great chapter, of course, very dear to my heart. I think you do a really good job on the history of motor cortex. I mean, it's a tour de force, actually, going from, Fritz and Hitzig to Ferrier to then going on to Kalaska and then going on to sort of what Churchland and Chenoy have done. I mean, it's a very nice encapsulated history of thinking about motor cortex. And then, I kind of love the last paragraph where you kind of say, we're still not really sure, right, what's going on. But I would say that the bulk of your book, and we'll wait till the end, is really sensory, it's either neurons, sensory behavior, or motor. And there's not that much psychology in it. Okay, in other words, that quote of Sean Carroll's and the word mind, it's not really what's in the book until you get to the end where neurons disappear from sight. Your whole chapter on rational decision making has no neurons in it. So I was wondering if you thought that there are like these orthogonal axes where we can think thoughtfully from single neurons all the way to behavior. But what we do the math on changes. And in your book, the math gets done on behaviors towards the end, and it's done on neurons in the beginning. And as you may know, with David Barat, we wrote something where we thought that probably when it gets to the final chapters, if we ever get to a neural version of those final chapters of yours, minus, the Schultzian little piece, that there'll be second level explainers that will want to do math on more psychological objects like you do at the end of your book. That we're not going to end up having a book written by Grace Lindsay in 10 years where those last chapters will be as neural as the beginning chapters. Do you think that's fair, or do you just think that the beginning of your book is more mature scientifically than the end of your book?
Yeah, so I will say this idea of using the word mind and that being controversial has come up. I would say that, I think it is relevant to point out, the Mcculloch and Pitt stuff about killing dualism and all of that, and the using mathematics and a computational framework to show that you can connect the brain and the mind. And so to me, using the word mind, but then talking a lot about neurons, it's kind of like, well, I do think that they're very connected. The chapter on memory and Hopfield networks is about how neurons connect, but it's also about memory. And that's a very cognitive mind kind of thing. So I think it is kind of core to computational modeling that it does try to connect those things, or at least it can be used for that. Obviously, the single neuron models are just single neuron models, and they're not, most of the time, they're not used for that connection. But there is something to the way that mathematics has been used a lot in neuroscience, that it is trying to connect to computation and to what has been called the mind. The idea that you are just kind of using separate math when you're modeling the behavioral level versus the neural level. I think that's true, and I think that's fine, because it's just a general concept that, when you have a lot of data and you are trying to get a hold of it and all of that, it can be helpful to build mathematical models. But then at the same time, the frameworks that you get from finding mathematics that explain things well on the behavioral level give you concepts to look for in the neural level. And I think reinforcement learning, and the chapter on that is, kind of the canonical example of this. Like, we had this interaction with computer science that led to this whole framework for reinforcement learning that originally came from behavioral studies and behavioral data. And then it went back to neurons. Once you identified something like a prediction error, you could see it happening in neurons. So I understand that there's these, like, the concept of different levels of explanation and all of that, but there are people who are interested in exactly the connection of how does this population of neurons make it such that behavior can be described with this mathematics. And that's kind of different forms of mathematics all the way down that allow you to make that connection.
Yeah, and just to finish, I don't have a problem with the link. I think you told, I love the way you say in that section on reinforcement learning that this is not the end of the story, and then you flip over and you tell the story about what Terry and Peter were doing and the work. Yeah, that's all fine. Although I do think that, the sort of reward prediction error in the sort of framing of sort of model free reinforcement, then your very nice treatment of value functions and being able to do away with the notion of planning, at least in that formulation. But I do think that we keep slipping away from, there's one point when you talk about the ring attractor, in Drosophila for head direction. And then you go on to say, well, this could be how ideas are held in the mind. It's a bit of a leap, right? Going from heading direction in a ring attractor in Drosophila to ideas in the mind. What I'm saying is that it's a bridge that we haven't crossed, right? In other words, you know, it seems like we're always getting quite concrete sensory motor model system versions of these phenomena when they're at least in terms of the neurons and their connections. And then it's a little bit of an analogous leap to then go, well, this might be how ideas in the mind are held. We don't know, right? So I was just wondering whether that's more of a hope on your part you can get from a heading direction in a Drosophila to ideas in the human mind. Isn't that just a little bit of a neural leap too far?
I might need to know your definition of mind, or at the very least, would you consider studies that look at working memory in primates and kind of assume a similar attractor type network at play? Are they studying the mind? Is it okay if
I absolutely
memory color?
Sure. I think that there's one point in the book where you talk about beliefs, desires, intentions, and that's sort of a part of, you know, philosophy of mind. It's a lot about, they even call it, you know, BDI, beliefs, desires, intentions. And it seems to me in a way, and again, this is not, that BDI slips away in this book, right? In other words, where the sensory motor end, you're absolutely right. There's some working memory component. Again, I'm just wondering, do you think that when if this book were written in 10 years' time, would we be able to write a similar kind of book with a little bit of neural flavor for BDI, beliefs, desires, and intentions? Do you think we're on the way to that with this treatment, or not? I mean, I'm not being polemical. I'm just genuinely interested where that some people might go, we'd like a BDI version of this book on model of the mind.
Can I add one thing to that maybe? So I think one thing, Grace, that in computational neuroscience, whether somebody is a cognitive computational neuroscience person or a systems computational neuroscience, their idea of the mind is different. Even their idea of, forget mind, their idea of memory is different. Their idea of working memory is different. Their idea of episodic memory is different. Their idea of what a circuit might mean is different, or how low level a circuit can be to be considered a component of memory, functionally speaking. So I think that on some level, and this has created obviously a little bit of a challenge and I think that John's question is reasonable here, given the title of your book is Models of the Mind, not Brain. So speaking of that, the notion of the mind, very many of by very many people in our field that I really respect them, is very limited to a particular very, very simplified choice task behavior in captivity, and looking at a particular small number of neurons in a small number of regions in the brain, probably just one region actually. And so and then sort of diminishing it so much, and then only allowing this to be the notion of memory, and then focusing on that and guarding it, so to speak. I think that's the kind of the, let's call it like diminished mind or something, because I don't think that's really mind we're talking about. We might be talking about some mechanics of particular sub-functions of the mind, but I don't think like we can even call that memory entirely. There are people who are on the spectrum from this kind of like very low level circuit level, which is totally fine. It's just not mind yet, but it's totally fine to do it. It's necessary to do it. Not that there's anything wrong with it. To the spectrum of being completely focused on, let's say, John likes to use the term BDI. Well, obviously, I would rather use terms from cognitive neuroscience, cognitive computational neuroscience, but also like, you know, anything in between. Let's say somebody's working about, I don't know, like long-term intentions or something like that, which is a term that's, you know, I use in my work and philosophers use. So that term is common. I think desire is a little bit more difficult to handle. Belief is also a little difficult to handle because of its overlap with the notion of belief, Bayesian belief. So it's a little bit hard to figure out what we mean exactly. So let's say long-term intentions, which is something that we think particular types of brains are not capable of, right? When we are talking about that, we don't just talk about one circuit. We might need to talk about networks. We might need to talk about function. And it's not just one behavior. It's a batteries of tasks. I think that in addition to John's question, that's the part where I do wonder what you think if we actually want to approach models of the mind, to what extent do we need to go to that level as opposed to circuit level or just sensory level computational neuroscience?
Mm-hmm. Well, it seems though like, yeah, I guess I'm trying to understand is if someone says they're like studying the mind and they study a very simple working memory task, maybe even in a fly or something like that, is the problem that they're just studying such a tiny component of the mind that it's not that interesting to say that they're studying the mind, like they're not going to learn general principles?
No, you froze, by the way. I hope that.
Yeah,
John,
Grace froze. I see her frozen too. Yeah,
okay,
let's wait.
so let's see. Grace, do you see us? You froze. We heard your voice for a second. You're frozen currently. Okay. Now
Grace is back.
Okay, now I can hear and see you guys. Okay.
Yeah, you're back.
Okay.
You're back, Grace. You're back.
Wait, I hear Grace, but I don't see her. Do you see
I see her. I see her.
Okay, so it's going to come back for me too soon.
Oh, she froze in.
Hello?
Sean? Or
So we hear you, but we can't see you. I don't know if you hear us. Do you want me to? Okay. Let me text you on Twitter. Okay, I will kick you out and then re-invite you. I will re-invite you, Grace. Remove and re-invite. Yes.
Okay.
Okay, you're back. Perfect. So what you were saying last is whether what I'm saying is that it's not interesting if somebody
is it just that they're trying to make generalizations from a very specific tiny part of it? Because people will study simple cells in visual cortex and say that they're learning about the brain. It's like, no, you're learning about simple cells in visual cortex. So it happens with brain as well as mind, just the idea that you can't extrapolate from a very
I do think there is a difference. I think if you're studying let's say that you're studying a particular kind of, let's say if you're studying 5 kinds of birds, you're still studying birds.
Mm-hmm.
But if you're studying, let's say if you're studying particular properties of metals, you're not studying money. I think that's the difference here. In order to say somebody's really studying money, if they only focus their time on studying a particular type of credit card, they can't say they're really studying money. Or if they're only studying nickels, they can't, and like let's say nickels and dimes, which is not just one kind, they can't say they're studying money. They can't say they're studying coins.
Mm-hmm.
They could say they're studying credit cards, but they can't say they're studying money because that has a whole other kinds of dependencies at a very higher level systems. And so I think mind is like money in this, or economics in this case.
Mm-hmm.
And just by studying the properties of nickels and dimes and how a coin is made, let's say, nobody's going to understand the economy entirely.
Mm-hmm. But could you understand anything about the economy from studying nickels and dimes? If there was a shortage of nickels and dimes that could impact the economy. So there is a connection there.
But there would be...
That's a different kind of thing than studying the particular, how the coin is made or a particular. So if you're studying the shortage of a particular kind of coin, you're looking at a system that is much bigger than just that particular shop that's making a coin. It's much more global, and it's looking at dynamics over a larger period of time and compared to other things. Compared to what? It's shortage compared to what? Like, are other things being produced or not? So that's looking at a lot of other kinds of relations that's not localized to just nickels and dimes, or it's not just local. So that's not the notion of money. Do you understand something about the notion of money if you study nickels and dimes? Something. Is it really what matters the most about the function of money? Not really, because the function of money is not reliant at all on the particular nickel and dime. And if you remove nickels and dimes entirely, the notion of money will still exist, which is similar to a point that I think Javier made earlier in here. He said, it seems to me like understanding the brain and understanding the mind are increasingly divergent questions, because who says there needs to be a biological brain to have a mind? As a functionalist, I tend to agree with that. Although I do think it's important to study the brain to understand how the mind's evolved and everything. So I will be a little lighter than the comment that Javier made. But I will say that the function of money is just at a different level of explanation, and it requires far more systemic and global levels of understanding than focusing on one type of credit, like the material at the physics level of nickels and dimes or one kind of credit card.
Yeah, I think, to Ida's point, I mean, she zeroed in on exactly, is I think that, mind is complicated to define. I mean, I think that, it's very much wedded to the idea of the mental. And I think that when people think about mental, they think about the expression, formation, and function of concepts, the ideas of desires, as we said, beliefs, plans, reasoning, thinking. And I just think that it's just interesting that in your book, that when we get to the part that's closest to that in rational belief, there are no neurons. Right. So I'm just saying that, to Ida's point, it may well be once you get to the things which are most closely allied with the notion of mind, the objects upon which you do your mathematics are more global ones, like Ida said, when it comes to thinking about the economy, you just do not need to think about the material objects. So it's more like, either intentional or unintentional, interesting thing that as one got the closest to the mind things, and then I agree with you, memory sort of straddled in a way. You very nicely talk about Hopfield, and then you talked about the ring attractor. It was more sort of whether one day there'll be a more neurally fleshed out back end of your book, or whether it will always be that the neurons become like money, that Ida's saying, yes, they're the second level underneath, but the first level explainers will be more psychological, just like at the moment they are in your book. It just seems, are you just showing the shape of the subject? Or is the latter part going to get more neural as we advance?
Yeah. Now, to be fair, the book about kind of Bayesian psychology, I was going to have a section about how people think that probability distributions are encoded in neurons, but it just didn't end up having the space, and it was a little too technical.
Which is the only way we think of the mind either. So
yeah, but still, I get it.
It means that it could get more neural, but I think it's also, to me, this is just different people have different questions. So yeah, if you want to understand kind of how society works or how groups of people work, you probably don't have to go down to the neural level. You can think about things more in people have traits, and when these kinds of traits interact, this is, likely to happen. People think about this when they're trying to organize companies and that kind of stuff. There's just different questions that people have.
But we're saying that for the mind itself, though.
Just to be clear, yeah, nobody's going there. So let's throw away the straw man. We're not talking about that straw man. We're not talking about company organizations or social. Nope, that's not what we're talking about. Let's come back.
We're talking about the mind.
Just the mind itself. There's some question you have about the mind. You don't just say,
cognitive computational neuroscience.
Yeah, but so when you say studying, a simple working memory test isn't representative of the mind, I think what you're saying is it's
not representative of even memory. I'm sorry, I'm gonna even make it worse. Studying one small working memory task in the fly, it's not even at all anywhere close to be representative of memory or models of memory. That's what I'm saying.
Okay, but what is it that it's lacking? It's lacking connections to other things, right? Connections to other part of the brains, connections to the body, and connections to things outside of the body as well, right?
What does it mean honestly, also, when one of the things that people like to do at that level is then let's generalize it to human minds. And it's like, we have many different kinds of memories and different organs of memory compared to a fly. The models that are happening there are very different. Birds and bats and humans just have very different kinds. And it turns out that bats and humans might have more similar, for instance, but fly, for instance, might have a very different notion of memory, working memory. In creatures that have a working memory that lasts 2 seconds versus creatures that working memory might last 10 seconds, there's a huge difference. So there's qualitative differences that are very significant in memory and in global behavior and mental capacities or mind capacities of a particular species that really, if you look at it, is it's basically a accumulation of different kind of smaller level differences in basic operations like memory, like episodic memory, like long-term memory, like consolidation.
The conclusion I'm getting from you is that we should not have a word memory. We should have very specific.
No, not at all. When did I say that? That's another.
Well, that's what I'm drawing from what you're saying.
let's throw away the straw man. No, that's a wrong conclusion.
You're saying that the memory in a fly is different than the memory in a bat, that's different than the memory in a human, and this kind
maybe
of
it can
memory.
help.
No. So John, give me a moment. Give me a moment, John. No, that's not what I'm saying. So let's not create a new straw man. Let's focus here. I'm saying the memory in the fly cannot account for all the notions of memory in humans.
Sure.
And when anyone talks about mind or tries to get grants about minds, for instance, or sell something in the name of the mind, people as humans, they think we're talking something that can say something about human minds. They don't think, oh no, we're just talking about one task in flies. That's not something that is usually advertised at the highest level. People start by showing a family photo and saying, think about how important your memories are. And then like by slide 5, you realize we're thinking about just like one short, working memory in flies, which I respect a lot. All I'm trying to say is that it's not generalizable to all notions of memory. And one can say, I am studying a working memory task in the fly. There's no reason for the person to claim, I am studying the mind. Like, it can be very specific. It doesn't. So that's the point that I think I'm making. And I think that's the point that John was making to some extent, which is that there is a difference. And there is a reason. There is the word memory. It has a history. It has a very rich history. I happen to love its history. Many people have written fantastic books about it. There's mathematical models of memory, many books on it, actually. Comparison across species between rodents, primates, humans, various kinds of memory, episodic, working memory. How is it different in creatures that are more visual versus tactile? How is visual working memory, verbal working memory different, etc.? There is a rich setting. So nobody's throwing away the notion of memory. One is saying enrich it. And don't claim you cover all of it by claiming a part of it, right? That's the point that I was trying to make. So let's not enter strawmen that want to get rid of the notion of memory, because that I don't want them. And let's not enter strawmen that think mind means studying the entire society. That's not what I'm saying either. So between that range, I think that's the point. And at some point we should get to questions, because there is
just one. Yeah, I mean, I think, to be fair, Grace, the induction is always difficult, right? I mean, we're always faced with this in you're absolutely, action potential in a squid giant axon. We have every reason to believe that the action potential works in a similar way in a cortical axon, right? So it's a very interesting issue. When can we feel more comfortable with the induction? And then as things get more mind-like, as Ida's saying, the induction gets more difficult, right? I don't know exactly why that is, but it seems as though the induction gets more difficult. I mean, no one thinks the atoms that our brains are made out of and the brains of a fly are different. So the more fundamental the building block, the more obvious the induction. And then you get into these cognitive domains. And then I think you'd agree, the induction becomes difficult. And then we have to be very careful. Again, I think this is what Ida's saying, is that the words begin to become more like metaphors than facts. And we have to know, when are we in a metaphorical domain and when are we in a genuine inductive domain? So just my last question for you, because, another thing about your book, which I really liked, was you're very diplomatic, right? You're basically not really, you don't come down gushing, but you're quite ecumenical. And I was just going to wonder, the one section that I thought I'd really like your opinion is when you get to the graph theory section, where you talk about the ability to quantify connectivity, and you talk about spokes and hubs and rich clubs, and I think it's quite interesting, and this is a criticism I've made and had very, I hope, friendly discussions with Danny Bassett, is it goes from being a set of metrics to those metrics being correlates of diseases. And most of your chapter takes those metrics and explains how they may be abnormal in Alzheimer's and schizophrenia, for example. But what doesn't happen is how these things have actually conceptually helped us understand the mind. And you actually finish your section, if I remember correctly, sort of seeing it more like a biomarker, right? So I was just wondering, so far, I haven't really seen how throwing these metrics at brain data, either macroscopic or microscopic, has actually given us a new concept of how the mind or the brain works, outside of it being a biomarker and a correlate of disease. Would you agree? I find myself struggling to see what we actually learn conceptually in a way that I think we do in almost every other chapter that you wrote. I felt, yes, I feel like I've grasped an idea. Do you agree, or am I being too harsh?
No, I understand what you're saying. And as I said, I wanted the book to reflect the areas where there is connection between mathematical methods and neuroscience. And this is an area, this is a very direct application of, a broad area of mathematics and network science to the brain. And I understand the motivation to do it, because you do look at the brain like it's connected nodes. So we should take the math that's used for things that are connected nodes and try to use it to understand the brain. So I very much understand the motivation, and I think with the development of more sophisticated kind of graph theory-based techniques that are designed specifically for understanding the flow of information in neural circuits, we might be able to get farther with it. But yeah, right now it is kind of taking these pre-existing metrics and seeing what they correlate with. And that can work in the biomarker sense. But yeah, you kind of hit a wall with where you can go with that pretty quickly, especially when some of these metrics are kind of so broad and show up in so many places that it's almost like, what are we learning by seeing that this network is a small world when so many things are small worlds,
Yeah.
So yeah, I agree that there's a sense, at least to me, of like, yes, this sounds like a great approach to the brain, but then so far, it's being explored.
You say that. I mean, I just worried that in that case, the hypotheses almost end up always being couched in the language that the metric spits out. Mm-hmm. So it ends up being kind of circular. Yeah. Right. But okay, well, listen, the book is fabulous. I hope everyone is more than convinced now that it has to be read. And I think it's really a great snapshot of the state of the art right now. And I think the progression from the beginning to the end is the progression from single cells to psychology, with still an open question how we're going to have neural level granularity for psychological concepts. It's a really interesting thing in that book. So, okay. So, oh, look, Melanie, it's been ages.
It's so great to see you. It's like the Salon is not official until you show up. It's so wonderful to see you.
It's great to see you. Hello. I was so thrilled to be here again. Grace just disappeared.
Oh no, I can.
Oh, Grace is here for us. Yeah. We see her and we hear her.
Okay.
Hi, John. We see and hear John as well. John, I'm going to mute you until Melanie asks her question. Melanie, do you see Grace?
I do not see Grace. I see an icon.
I can see and hear Melanie. So.
Do you hear Grace?
I do hear Grace, yes.
Okay, perfect. Then you can ask it, and hopefully, at some point, a video will show up.
And we can give you the odd description of her as you want.
Yeah, let me know about her.
She's smiling.
Expression. So, my question is about the role of feedback connections. So I know that you mentioned Hubel and Wiesel and their inspiration in developing the sort of the basic architecture that people in convolutional neural networks adopted, which is completely feed forward. And I'm wondering if you know sort of where the notion that a feed forward network would be sufficient or be the thing that sort of computer science, AI, machine learning should focus on, as opposed to feedback networks. Sort of what did Hubel and Wiesel know about feedback connections? What do we know now about the role of these connections? What should we do in machine learning? Should we try and work harder on developing networks with feedback?
Yeah, so Hubel and Wiesel say explicitly that their model is, like their little sketch of how the visual system works is, limited. They're focusing on specific things and they're ignoring a lot of other things. So I'm sure that, they're certainly aware of the fact that the responses were dynamic over time, and you don't get that from a static input without some sort of recurrence in the network, or something internal to the cell at least. So I don't know what was known precisely about the anatomy at that time, but surely they knew that there were other influences impacting the neuron than just this feed-forward pathway. I think the idea in the neocognitron to just translate it to a feed-forward pathway is just taking what Hubel and Wiesel were highlighting and assuming that those were the most important bits and moving on from that. And then, it is the case now with the way that we train neural networks that having, a feed-forward network can be better than having a recurrent neural network, because if it's the same depth, but you add recurrence, you're just adding more time steps, and you need to train through that, and it just makes it harder to train. So I think there's a lot of pressure and motivation in machine learning now to keep them feed forward. And you see that in like the transformer architecture and all of these things that make these very elaborate but still feed forward networks, because they're easier for our current methods of training them. My personal research is actually on adding recurrence to convolutional neural networks right now to study them as models of the brain. So I agree that that's an important component to understand and to include in models, but there is this divide between the goal of machine learning and the goal of computational neuroscience. So I wouldn't even necessarily advocate that machine learning should be adding these recurrent connections, even though I know they're very important in the brain, because I understand that maybe it's not the most efficient way for machine learning to solve the same problems now. So I think maybe if we get training the neural networks and just kind of can add more details to them such that they're closer to the brain in the ways that are relevant, then maybe it would become more efficient to do things with recurrent connections rather than super, super big feed forward ones. But right now they're kind of different enough, especially in the way that they train, that I don't know that recurrence is going to be the most fruitful short-term application in ML.
Well, yeah, I understand it's hard to train recurrent neural networks, and they're inefficient. And even what we call recurrent neural networks are barely recurrent. They just have a very kind of limited amount of feedback and over a few time steps.
Yeah.
But it just seems like the deep neural networks have all these issues of brittleness and generalization, vulnerability to all kinds of weird kind of perturbations that you can do, and they just are not very brain-like. And maybe one of the problems is that they don't have this dynamics, they don't have this kind of feedback that we see in the brain. And I don't know if that's the limitation is how hard it is to train such networks using something like backpropagation, or if there's just some view that the Hubel and Wiesel neocognitron architecture is kind of a frozen accident that has just propagated through history.
Yeah, I mean, I think there was a period of people adding recurrence in machine learning, and then it got replaced with things like transformer architectures, which were doing better. So I feel like people did, kind of very naturally look to the brain and be like, here's a major architectural feature that we're missing in our models, and try to add it, certainly with kind of attention-based models where you have a part of the network that modulates the neural activity and another part of the network. Those are recurrent processing units in the way that they were originally done. But then, yeah, I think they just, at least, in this present moment, have been superseded by non-recurrent methods that are trying to do the same thing. But, tomorrow somebody could come up with a good recurrent architecture that also trains really well, and then there'd probably, be a big rush to putting recurrence back in. So yeah, I think yeah, the fickleness of getting them to work and kind of the scoreboard nature of machine learning, where it's all about that extra percentage point in accuracy, I think is, that's not going to necessarily push ML people to really focus on the basic principles of how the brain is solving the same problem.
Yeah, maybe to their detriment, ultimately.
Yeah.
Can I just add a coda to that, Melanie? So Grace, can I just understand, that's very interesting what you were saying. Are you saying, I think what Melanie was saying, that if we want to become more brain or mind-like, then recurrence would be a good idea. But I think what you're saying is if we continue to do the kind of benchmarking that AI is currently doing, then, and let's say that it's still mainly classification and those kinds of things. I think, am I right to say that what you're saying is that if you're on that train and you're still trying to do that kind of work, recurrence wasn't the magic bullet. It turns out that you can do transform. But it seems like a slightly different question if we're staying on this track of benchmarks and, Go and Atari and, speech recognition and image recognition, and that track, maybe you're right. But if you wanted to do other things that were more mind-like, maybe we don't know whether including recurrence would be the best way to go. Would that be a fair, and that's my implication, understanding of what you were saying?
Yeah, I mean, a lot of the things that we think recurrence does in the brain, for example, what I'm studying now is kind of how it makes us robust to noise in images. You can, at least in the settings that we have and the data that people use, you can train a deeper feed-forward network on like the rough noise distribution that you are considering relevant, and it'll do great. So if you give it the training opportunity and you give it enough depth, it can do fine. Or you could try to train a recurrent neural network to do that. I mean, a recurrent neural network, the way that they get trained is that it gets unrolled in time to be a deeper network with the same network repeated for each time step that you run it. So there's like a literal equivalence there. The recurrent network is just more constrained because it has to use the same weights at each chunk, where if you just made a deep network, it could move its weights any way it wants. So it's not surprising really that you can get a deep feed-forward neural network to do the same thing that a recurrent neural network does, at least in these very kind of the very simplified way that we're representing recurrence. There's a formal equivalence there. And that includes on for tasks that that we think recurrence in the visual system is used for. So I don't think it's like that the ML people are so like using the wrong tasks or something. I think it's just there might be more than one way to solve the problem.
Great, thank you.
John? I don't think we can hear you.
Okay, now I'm unmuted. I unmuted myself. Yeah, so frame the question. Are you familiar with Vizaki's The Brain from Inside Out? Because that's one way of framing this issue.
I haven't read it yet.
Well, roughly, I mean, there's a habit of looking at behavior and things in the outside world and looking at neurons in the brain and see there's some correspondence, say that must be the answer. But I think he's arguing, yeah, I guess you have to do that kind of thing. But much more important is to look at not only the neurons in the brain, that may be simple cells or play cells or something like that, and then look at how they get their inputs and what they do to their outputs and how that information is transformed. And to a large degree, that's been secondary, especially in psychological studies. And I think he's pushing that kind of thing. And it came to mind particularly to study about mind and neurons and things like that. So there's a role for computational neuroscience to help this out, I think, is to say, well, one implementation strategy would be this, where we find this at the next neuronal level. And or computational neuroscience can say, well, there are 5 ways this could be implemented at the next stage. Let's look at that. Is that in your way of thinking about it, what the role of computational neuroscience should be in its collaboration with more standard neuroscience?
I think that's definitely one of the roles. Yeah, I think it can play many different roles, but certainly the idea of thinking about how information is transformed at multiple stages of processing in a neural network is very core to what people do when they build these models, when they build multi-layer models, or even when they build kind of smaller scale, more experimentally grounded models. There is this question of, why is the information represented the way that it is here, and where is it going? And a lot of times there is a bias to focus on a single area in the brain at a time and not necessarily think about where that information is going, or at least not be super explicit about what your assumptions are about where that information is going and kind of what the neurons there are doing with it. And I think that can be a problem, because that is what matters. What matters is how it propagates through the brain and eventually leads to behavior and all of that. But I actually think that bias comes more from the history of the experimental literature, where it's just very difficult to record from multiple areas at once, certainly to record from an actual cell that's receiving input from the cell that you're recording from in the other area. It's just the electrophysiology history has been record from 10 neurons in this one brain area while you show stimuli on the screen. And so that's going to bias then the computational approaches to understand that. It's natural then to just be like, okay, let me relate the stimulus to the neuron's response, right, and let me only think about the neurons in this area and not how they go to other areas.
That came to mind when you showed Hubel and Wiesel's model of projection, and led to the simple idea, oh, we got these cells in lateral geniculate and they would project in this pattern. And the Japanese scientist, whose name I don't remember, said, why aren't they doing that next? My impression is that hasn't been demonstrated, that we really don't know where simple cells come from.
Just as a point of...
Yeah. Sorry.
Yeah, I could be wrong. It's not my area. It's not. It ends up always being more complicated than it looks on the surface.
Yes, and that's partly to do with the recurrence, actually.
And actually,
you don't just get the feed forward input.
In Grace's book, John, Grace at many points in the book actually points out, Buzaki's main point, just for people who may not have sort of read the book, is he's very much against this sort of correlating an outside stimulus with a neuron and calling it a code, right? And Romain Brett wrote a whole BBS article on this. There's this concern that just because you as a third-person experimenter can find a correlation between a stimulus and a neuron doesn't mean necessarily that's being used by the brain. And I think in several places, correct me if I'm wrong, Grace, you actually make that point, that be careful not to think just because you can find a correlation that that's actually being used by the brain, and use some nice examples of that, if I remember correctly. And what he wants to substitute in place, John, right, is to say there's a lot of endogenous patterns of activity inside the brain already, and then they kind of latch onto a behavior or onto something in the world that is meaningful, and then that's the way that internal endogenous circuit was there all along acquires functional meaning, and so that's why he calls it from the inside out, right? So
to qualify Buzaki, I'm not sure what he says in the book. He uses external variables. He uses head direction and place as important variable. It's not like he said, don't look at that. It's just
he just doesn't believe in the sort of decoding notion that is so where the outside world is correlated. And I have a lot of sympathy for that view, but I think that it's kind of, if I understand Lindsay's book, it was kind of neutral to that point, and admitting that sometimes these correlations are not actually used by the brain. I can't remember exactly what was one of the examples you gave, Lindsay, right, where you said that was actually sort of almost like a false conclusion to reach if you're not careful.
Yeah, I think you're mostly thinking of the chapter on information theory, where this is, most explicit, that people are thinking about what is the code and what's being encoded. And there was an example I gave about retinal cells, on and off cells, that they were able to manipulate the signal in the on and off cells experimentally, and basically show that there was information in the firing of the cells that the downstream circuit wasn't using and should have used if it could have, because it was valuable for the animal to do the task it was doing. But it just shows that just because you can find it there doesn't mean it's being used later.
Right, exactly. Right. It only used one of the on cells, right? Didn't use the off one at all. Yeah. Right.
Thanks a lot. So you should use the external variables, but not take them as the gold standard. They help you guide towards what is working and not. I'll sign off.
Thank you.
Thank you so much. I think the most voted next was John Roski.
All right. I've tried to unmute myself. Can you guys hear me all well enough? Oh, amazing. Okay, good. Hi, Grace. Thanks. I liked reading your book. So I'm just in your presentation. I was kind of struck by a thought that's kind of puzzled me for a while, which is that it seems like in the first, few decades of work on mathematical theories of neuroscience, there was this interplay between people who were looking at symbolic models of computation and people who were then looking at sub-symbolic or distributed or whatever term, people invented every 30 years or whatever, right? So you had like Turing inventing a model of behavior, which he would call the computable functions done by Turing machines. Then Mcculloch and Pitts instantiating that in neural circuits. And then Kleene showing, well, no, those don't do Turing machines. They in fact do finite state machines. And then Rosenblatt saying, okay, let me integrate that with Hebb. And then McNaughton and Papert saying, oh no, perceptrons are weird. And Minsky and Papert showing, yeah, they're even weirder than we thought. So it seemed like there was this real productive conversation. And nowadays, it seems like the opposite is happening. You get people saying like, oh no, everything's symbolic, or no, nothing is symbolic, everything is distributed. And then people having to make these claims like Gary Marcus does, like, we need hybrid models. So it seems like the discussion has just become a sort of talking past each other point. I'm wondering what you think about this, or like, since you've done this broad overview, like, do you see why this has happened, or like, and also do you think that there's any ways that you could get out of this, or are we just sort of doomed to one or the other.
Wait, 1 second. So do you mean like, so Gary Marcus said that in like 1999 or something, right? Or since then? So when you say nowadays, do you mean in the 90s or do you mean now?
Well, I think he still says it, doesn't he?
I think he
Oh,
still
no,
said it.
Yeah, he definitely says do the hybrid, but you're saying nowadays people are saying either this or that, and nowadays Gary Marcus is saying hybrid and saying this seems like
Oh, yes.
late
Yes.
90s,
Yeah.
right?
So,
That's what you mean.
yeah, late 90s to, it seems like we've moved away from, not one event, but we've moved away from having a period of like productive conversation into everybody just yelling at each other and talking past each other on these issues. So like what I don't know, what do you think about it? Maybe you have a different opinion. I don't know.
I kind of thought, though I didn't actually dig into this, that the kind of pitting of symbolic versus distributed was sort of really, that dichotomy was dug out in the AI side, because it was, people had to decide what method they were going to use when they were building their systems, and certain methods were performing better at any given time than the other one. And so you got these kind of camps that developed expertise in either side. The application of that kind of debate to the brain has always been a little confusing to me, because we know behaviorally that like human brains do what people call symbolic processing. And we also know that brains are mainly made up of neurons. And so it's just like, it has to be a hybrid model at some point. So the notion of like, how, the fact that modern deep neural networks do struggle with what are normally called more symbolic tasks is a relevant thing to be aware of about them and to study and to try to make them better at. And, we could do that in a route that actually combines the two different classes of AI models, where you use a deep neural network to encode something into a symbol and then use it as symbols in like more traditional programming. But the brain has to use neurons for the whole thing. So I feel like at some point we're going to have to come up with a model of some sort of neural network that can do symbolic processing well. So I think this kind of has a relation to the idea that the AI side has different goals and different constraints, and you have to make your choice of how you're implementing something. Whereas to some extent on the neural side, it's a little bit of, how do you want to talk about what's going on? Do you want to talk about the symbolic processing? Do you want to talk about the distribution of neurons that are encoding that symbol? Different questions in the different fields.
So I'll add to that in the domain of psychology and cognitive science, there was a linguistic dominance. There was a period of linguistic dominance, and that period co-occurs with the time where symbolic approaches are much more popular. And at the same time, it's not just that there's something from computer science that comes back to cognitive science. Cognitive science is prospering with neural networks, at least some people. And there is this wonderful talk that sort of compares the situation of the West Coast and the East Coast approaches. It was like East Coast was much more into symbolic with MIT and sort of Chomsky being there. And then the West Coast had a lot of neural networks. And we have the PDP book coming out of the West Coast from various people there. And we have people like, for instance, let's say John Cohen, who got sort of trained in the West Coast, but then moved to the East Coast. And then like you have like a lot of people who get trained in this tradition of neural networks. But this is since the 80s. Their early papers on like the Stroop task and everything is in the 80s, and they keep publishing. The thing that changes is that in famous conferences, all of a sudden, there is a decade where you see a lot of neural network papers, and all of a sudden neural network papers are no longer accepted. And it's all like, more symbolic and linguistic. And all of a sudden there is a shift again. So there is the death of the neural networks and the revival and the death of symbolism. Now these days, do you see anything at NeurIPS that's like symbolic that you can remember? Do you remember talks there or something? It's like, it's almost like, it's well, like a shift that happens.
I guess I meant something different. So like, for example, Kleene invented regular expressions to be a mathematical theory of what Mcculloch and Pitt's neurons were supposed to do, because they didn't give one. There's no proof in the Mcculloch and Pitt's paper. But I don't know anyone today that would say, like, if you use a regular expression, you're using a neural network, even though that's literally what they are, right? They are regular events. I mean, I think the paper even says that, regular events in finite neural nets or something. But I don't know that anyone would say that these days. Like it's just sort of accepted that that's now a symbolic method, even though it was originally a neural method. So, but now it seems like there's this there's this weird tension.
Yeah.
That just sort of like always, yeah, like you said, right? Would you see something like that at NeurIPS? I doubt it.
Yeah.
I'm not sure. Yeah, so I don't know how to resolve it, but yeah.
But I mean, Ida, I think was instrumental in getting Paul Smolensky to give a series of talks at Microsoft Research. Tell me if I'm wrong, Ida, but it was you that made me realize that those talks, and they were very interesting, where Paul Smolensky himself very much speaks about the need to somehow get symbols that can be manipulated out of a neural network, just like Lindsay's, Grace is saying, is it, you're made out of the same stuff, and it looks like they're neural networks, right? So I think the way that one has to see this, and I think I've said this on this program before, right, which is sometimes connectionism is eliminationist. It says, look, we don't have to have representations or symbols. You can get the job done without them, right? Which must be true, right? No one's going to talk about symbols or representations in a central pattern generator, right? But at another point, the neural network doesn't become eliminationist. It becomes the implementational substrate for doing symbolic work, which is, I think, what Grace was saying. So in other words, at some point, we just have to not confuse the sort of eliminationist point of view with the implementational point of view. And it must be true at some point that we can simulate symbols on a neural network. I mean, it must be true because it's what the brain's made out of, right? So, but it doesn't mean that at the level of the actual phenomena, the kind of ones that Ida and I are interested in, that you're not operating on some kind of real simulated object that looks like a symbol or a representation. And I think we'd be much better off if we just didn't collapse eliminationist arguments with implementationalist arguments, right? And I think that that's where someone like Paul, if I remember at the end of his talk, Ida, correct me if I'm wrong, said, we're going to have to find a way on how to layer symbolic manipulations on top of a neural network architecture, right? And that seems to be the project. And, I defer to, you guys, to how much the AI community's come along of layering symbolic manipulations on top of a basic neural network architecture. But I can't see how it will be otherwise, right? In other words, it's going to have to look like that at some point.
I mean, to be fair, we're not there at symbolic, but something else has happened. Like GPT-3 is like, an example of something that's somewhere in between, and it's none of them. It is one of them. It's not exactly symbolic. It's not what we ordered, but it's what we got. It's like we thought that by this year we're gonna have flying cars instead Facebook changed its name to Meta. So that's like you never get what you really want sometimes. But it seems like GPT-3 is such a model, but in a very chaotic and non-principled way. It's not really trying to solve any symbolic issue or any kind of have a neural network that is the foundation of the symbolic processing, the way that we would want some latent space that is symbolic to be emergent on top of a neural network that's trainable. And that's something that we would desire, and we still don't have that yet. But instead, we got GPT-3. So it's not that it's completely dead, the intersection of those two areas. The intersection of the language logos people and the sort of distributed representations, neural network, PTP people. Like, I feel like the DNAs have sort of combined now, but the Frankenstein baby is currently maybe not what we wanted.
Well, if I can give us an anecdote from, so Paul did something like this in linguistics. He had created a symbolic theory out of a sort of neural network Hopfield-esque type of thing, and it became one of probably the most linguistically significant theories to come out of the last decade or century. But now what's interesting about it is it's totally become a symbolic theory. Like, most practitioners of it don't consider it a neural network theory anymore. So that's kind of why I wanted to see what you thought about this debate. But anyway, I'll cede the.
I wanted to briefly, ask you guys who have more cognitive backgrounds than me. The idea that you can get a neural network to do something that's symbolic-ish but is messy and chaotic. Is there a sense that for it to be human-like, it has to be very perfectly symbolic, because humans are messy and chaotic and not always good at their symbolic tasks? So I would be okay with if the best we can get for a neural network to do is not perfect symbolic computation, but something, you know, roughly getting at that, but messy and has heuristics and all of that.
I feel like for that question, we need Melanie back because she writes about this often. The issue of that one is that, let me put it this way. Yeah, is Melanie back? Yes, there she is. Melanie, you take this question. I wanted to make an example about what is the difference between the solving a task the way that GPT-3 solves a task versus actually like understanding or using true symbolic processing, but I'm gonna leave it to you.
But yeah, that's hard to say because we don't know how GPT-3 solves some of its tasks, right? You can give it a problem, arithmetic problem, and sometimes it will get the right answer, sometimes it won't. And like, why? No one knows. We don't know what its representations are, but clearly, you know, it's easy to break it. It's easy to make it spout out complete nonsense. So it's pretty clear, I think, that it's not understanding, but it's doing something symbolic, as you say. And I love your analogy of Frankenstein's baby. It's not what we wanted, but it's what we've got. And we don't understand it. And someone just asked in the chat, do we know how humans solve tasks? Well, I think we understand it a little bit better than we understand GPT-3.
I don't know what happened to Javier, so I'm just gonna remove and re-invite him because he disappeared for some reason.
I mean, my impression, you know, Grace, is that there are all sorts of ways to get behavior that sort of looks like human behavior without doing it that way, right? In other words, the kind of errors that GPT-3 makes is just not an error that a human would ever make, right? It's just, so as long as they're getting the questions right, it looks so reasonable, and then it makes an error and you go, oh, I've been fooled. This is a replicant, you know? Wouldn't you agree?
Yeah.
I mean, it looks human until it really doesn't, and then you go, whoa.
But is the assumption there that like there's some qualitative difference then in how humans are doing it, or humans and GPT-3 are just chaotic in different ways?
No, I mean, the whole point is that there is a particular way that's the algorithm that we know humans are consciously using. And, you know, we can talk about what algorithm we're using to generate these things. We don't know what exactly that is with GPT-3 in some ways. And it's not just about lowest layers possible. It's just the cost function is just predict the next thing. And therefore, anything else that happens in between, we don't know. For humans, you learn the grammar, you learn the alphabet, you learn certain words. There is a particular way that humans learn at that level. And how the neural networks allow for those higher level symbolic complex events and rules to be predictably happening is a different story. So one thing that Melanie was saying that I think is key is that when you look under the hood, we don't know what kind of engine is running the GPT-3 car. When we sort of try to, if you try to just like, you know, observe what kind of language they have. Also, if you put them in certain tasks or tests, you can see that they're not performing even behaviorally as well as humans. So there is a behavioral measure, but there is also the process, the algorithmic difference. There is definitely an algorithmic difference. We know that. And I think a part of symbolic processing is the algorithm part, so that there is a guarantee that in cases that you haven't been trained on millions, billions of corpus of texts, you can generate this new thing on the basis of the rules that you know. I think that rule-based, as opposed to billions of texts, destroy the planet 3 cars over their lifetime, or like, I don't know, million flights between here and Berlin. I don't remember the numbers exactly. That kind of training is very different from here are the rules, and on the basis of these rules, you can do it. And you happen to learn the rule with the help of some people who taught you, but also you picked some of it up, extracted from experience. You didn't need to see the entire corpus on the internet in order to be able to predict what's the next word, so to speak. So both behaviorally, algorithmically, and in terms of the types of neural network that are happening, GPT-3 is a lot more chaotic than humans.
Mm-hmm. Yeah. And yeah, even if we don't yet can say what the algorithm GPT-3 is using, we know circumstantially from how it's trained and all of that and the mistakes it makes. I assume we can eventually figure out the algorithm GPT-3 is using, describe it on some algorithmic level if we have, unlimited access to perturb and study it.
Sure, but it's not modular enough. Sorry to interrupt you. It's not modular enough to be the same rule-based, grammar-based way that the human algorithm is. But Melanie, go ahead. Sorry.
No, yeah, I was just going to agree. It's there's a whole subfield now of machine learning called Bertology, right? Which is the study of Bert, which is sort of like GPT-3. And GPT-3ology is hard because we don't have the source code. Although now people are open sourcing versions, non-open AI versions of it. But yeah, it's really hard. And Roberta, somebody said, yeah, it's really hard to figure out because there's no modularity, as you said. It's really hard to figure out how it's representing these things.
I mean, it just seems, the errors. I mean, you know better than I do, right, Melanie? Why don't you give some examples of the kinds of utterly idiotic errors that it makes, right? In other words, what's heavier, a pencil or a toaster? And it says a pencil, right?
Yeah,
in other words,
yeah. It has no common sense.
It has no common sense whatsoever, right? So in other words, and what do people say to actually deal with that problem is to go through a series of other objects so that it can circle back and then say, well, a planet is heavier than a pencil, and therefore a toaster is lighter than a planet. And then, it's just doing it through brute force and more data, which is fine, but we just don't make those kind of errors, right? It's just a different animal.
And one of the things I found frustrating about dealing with GPT-3 is this idea of prompt engineering. You interact with GPT-3 by giving it prompts. And that means you give it examples of the kind of thing you want it to do. And then you give it a new question and it follows the style of your prompt. But the way that you ask the question, it's extremely sensitive to that. And so there's this now field of prompt engineering where humans engineer prompts that will elicit the kind of behavior that they want, and it's not easy to do. So that's a clear indication that it's not understanding in the way that we're understanding because of this extreme sensitivity to the way that you have to ask the question.
I think generally latent states and how they emerge in a sustainable and stable way in neural networks, and what's the minimal number of experience samples that allow for the stable reproduction of those latent states in the representations learned by a network, that's a huge challenge right now. And that is something that would move us forward to the next level. Because when you look at people and how they treat latent states, at some point, everybody's doing a hack. So there's this and that, and this part of the paper in the future. And then we've been like that for now. It's like a standstill. We've been there for almost a decade that we're not enriching the latent states enough. There is every now and then there is a little movement, but we are so it's almost like we're distracting ourselves from the main issue for at least the higher levels. And I feel like once we figure that out, it would be helpful. And here are the kind of challenges these days. Some people have a guaranteed, provable way that all the latent states would be discovered. However, the assumption of this is that there is a policy cover. What does that mean? That the agent tries every possible combination of policy ever possible in that environment, which is not realistic for any biological creature. In some artificial environments, it's realistic, but not in all of them, not even in a, for instance, game. So that's a challenge there. There is a guaranteed mathematical way, and people are like, look, we proved. You're like, yeah, but you also need to explore everything and every possible policy. That policy cover approach obviously is not going to work. Another, there's then there is the other people who are like, oh, here we discovered a lot of eigen options, for instance, and you're like, oh, great, but you discovered too many. How many of them minimally are useful to solve the game in a reasonable way? And they're like, oh, we don't know what's the best way to find the main ones. We looked by the eye. So the human observer is constantly having to be there to supervise the situation, be like, all right, this and this and that are the useful ones. So we know that overall this agent will discover all of the relevant ones, but it wouldn't know which ones are the relevant ones, because it discovers 300 things, out of which 10 are the most relevant ones, and it wouldn't know which ones are those. So it's a little better than before, but it's still not solved. It still hasn't found the most relevant latent space of the problem. So moving there, finding that is important. And Javier, you've been here quietly for a while, so why don't you chip in?
Yeah, well, I love the book, by the way. I read it close to when it came out. I had it ordered from my local bookstore. So anybody thinking about doing that, you should. Yeah, my question / thought was a little bit more general, but I don't know if we've reached a point where there's kind of a divergence between what studying the brain and studying the mind is. And I mean, hearing what you were saying, Ada, you're talking about a neural network, but then you're talking about latent spaces, right? And I have the two views on the cognitive brain paper very fresh in my mind, John. And I feel like it's funny because even with neural networks, there's a study of the architecture of them, right? That's kind of what you're reporting. This is the architecture of the network. But then when you talk about latent spaces and representations, that's like a completely different question, it seems, right? Like there's the architecture component, which in biological terms is just like the brain, anything from, the chemistry and synapses and all that to, I don't know, interconnectivities between brain areas and all that. But then we're also simultaneously trying to ask, questions about representations and solving problems and all this kind of thing. And I mean, just now I was thinking, like, what if like Newton, when he saw the apple fall from the tree, was trying to start from like the chemistry of the apple rather than just abstracting everything and being like, this is a point mass, this is how we're going to solve the problem of gravity. I don't know if we just need to go in two different directions here to have each field be able to inform one another. Like we need to figure out how a mind works. I mean, we started with the brain because introspectively we have a mind. We sort of intuited that, and that's where we started. But it's just a mind, and even now it would be very difficult to figure out how an apple falls from a tree just by starting by the chemical structure of it. I mean, I don't know. I feel like that's why chemists and physicists deal with different problems. Can you go from chemistry to physics? Yes, but like I think there's a reason that they're sort of separate.
Are you saying that?
Go ahead.
Are you
Grace,
saying
it's
that
your question.
representations are the mind, and architecture is the brain? Or I just wanted to understand the point about representations versus architecture.
Well, I mean, I'm thinking on my feet here, but I think that we can use that as a starting point. Sure. I mean, I'm absolutely going to be wrong, but I think maybe that's like one way to start thinking about how to separate these different levels of analysis, I think.
Mm-hmm. Yeah, I mean, personally, I like the type of computational neuroscience I'm interested is partly the part that, asks how representations arise from architecture. So how do you connect neurons in such a way that they represent and process information in a useful way? So to me, those are linked. And yeah, you can study it in an artificial neural network, or you can study it in a biological brain. And so you can say you're kind of studying the mind of the artificial neural network if you're looking at its representations. And so it doesn't have to be brain specific, I guess. But to me, the fact that we focus on brains when we think about the study of minds is not just because of introspection as humans, but also because of observation of other humans and animals, and just the fact that they're doing such interesting things that it seems like there's some latent processing that's happening that we would like to understand. So if you want to study minds and you're not going to think about brains, the only thing you could do is try to create new minds, which is like artificial intelligence. But even then, you kind of maybe run out of ideas about how to go about that. And so it's natural to go back to the thing that is associated with the minds that you know and look at the brain. Because I understand there's some level where you can say, oh, you can implement the same thing in different structures. And, this is like Mars levels people talk about. But I think it's acknowledged that the implementation does constrain the algorithm. It constrains the representations. And so you can't talk completely implementation free about algorithms and representations. Like they are connected in a way where it makes sense to me that if you're really struggling with how a representation came to be or why it exists, that you go kind of to a physical level of, well, because the neurons are the way that they are, this is the representation that had to occur.
I think it's a little bit, Javier, just to get to your question, which I think is at the heart of many, many Salon discussions, right? And, I would just two things, right, about this. If you look at, Grace has in her book a very nice section on vision where she talks about these simultaneous sort of experiments, as if you want to call it that Nico Krieger's court did in Cambridge and Jim DiCarlo did at MIT, where they basically begin to show that you can have a neural network model predict the intermediate layers of a macaque physiological response, right? You wrote about that, right, Grace, in your book, right? So I think there are two approaches that are trying to bridge what you're saying, Javier. One, I think, which is more, that one that Ida and I are more sympathetic to, right, is that you have a behavior and then you basically try and model that conceptually with the idea of sort of, latent spaces, and you basically try and come up with an object which is conceptual at the level of the behavior. And then, no one has any objection to a second level explainer coming along at the neural level that is consistent with that first level explainer. But, we feel as functionalists that the first level explainer is the functional object, and we're perfectly okay with that functional object to be confirmed as existing in the constraint sort of way that Grace said, even though I think it's a little disingenuous. Usually it goes in the direction I think that we prefer. It's rare. I mean, look at the chapter on reinforcement learning. All that stuff came before the reward prediction error got found, and Wolfram Schultz probably wouldn't have realized what it was unless all that work hadn't been done on TD and other such things. So in other words, the algorithmic level of the behavior came before the neural implementation data, which is just confirmatory in my view. And then the other approach, the one that sort of Jim DiCarlo and others are doing, is say, okay, system level circuits, behavior, the intermediate object is a neural network. If we can look at the neural network and train it to do the behavior, then maybe if we examine that, we'll get a bridge between the implementational level and the behavioral level through neural network simulations of the behavior. Now, I think those aren't exactly the same projects. I prefer the behavioral, computational, functional approach, that Ida talks about, and then be happy when there's neural confirmation. I'm not such a big believer in the neural network as the intermediate between the circuit and the behavior. But these are two approaches that are very cool out there right now to try and bridge what you're talking about. Right? I don't think it's such a big deal, by the way, as long as you believe in this first, second level distinction, and that you're not going to have neuron A connected to neuron B connected to neuron C as your explanation of a prefrontal computation, then we're all fine, right? You have to have something in between, some intermediate explanatory object. So it's not that big a deal. I think it only becomes a bigger deal for me and for Ida when people think that you're going to have a circuit, A, B, C, D, and that's going to be the sentence you utter to explain some higher level cognitive function. That's where we feel that there's something missing in between.
I mean, it seems like the fear, if I can understand what you're saying, John, is that our solution to the brain is going to be a neural network that can approximate most of our behaviors and say, like, this is the answer. And everybody's going to ask, how does it work? And we're going to say, it works because it works. Like we've just, I don't know. I mean, we kind of need principles, right? I don't know. Maybe this is the problem with GPT-3 you guys were talking. It to some extent reproduces some of our behaviors, but what does it teach us, and how can we do it again in other domains?
And maybe that's the science that we are looking for. The science is, the engineering part is just imitate, but the science part of it is, how did you do that? And if it's about the science of the robot, you can say, how did the robot do that? But if it's about the science of the human, it's like, how did the human do that? And how did the robot do the same thing that the human do? Is it a functionalist similarity between them, or is there an algorithmic level? If it's just a functionalist, that's still imitation. In order for it to be a model of the, maybe it's a cognitive neuroscience, cognitive computational neuroscience plausible model, it needs to be able to show the same behavior or same errors, but also it needs to be able to show similar algorithms, similar neural processes for learning. And that will take forever to get there. So we can kind of like at least try, but it seems like just imitating the behavior, it seems like there is an agreement among a lot of us that that's an engineering solution. It's like, here is a task. I want to solve this task with a machine. What's the solution? It doesn't matter what the algorithm is, as long as there is a solution. But here is a task. I want to know how humans solve it. And I'm building the models to understand how humans solve it and help neuroscience and psychology study better to understand this. So I want to create a loop between models, behavior, and neuroscience to understand how humans do it. That's a totally different problem, where just solving the task as GPT-3 does is not enough.
I would also say, though, that, so I agree that, you can train the model and it can have similar performance. I mean, none of these models have perfectly, human-like performance and everything. And you can compare the activity in the network to the brain, and the fact that that matches, the fact that you can get better predictive scores on neural activity than any other models, that's a relevant finding. That hints that maybe it's doing something algorithmically similarly because it's producing the same kind of representations. But also there are some principles that you kind of get just directly from that, which is that you found an architecture and a task that is somewhat aligned with the architecture and tasks that brain area is doing. If you train a convolutional neural network on, auditory data, you can't predict the visual cortex very well. So the selection of the data that you train on and the tasks that you train the network to do and the architecture of the network, those are principles you can extract from kind of playing around in the space and seeing what gets you the closest match to the real neural data.
That's a good point. But let's also keep in mind that, we've known now for, I don't know how long, 15 years more, that convolutional neural networks are a good sort of approximation of the visual system to some extent. But it depends on how much we are being lenient in what we mean by that. You look at adversarial attacks, it actually doesn't look like human behavior quite, because it confuses very strange things. Then there are different solutions. There's at least 3 sets of solutions from Blake Richards and Irina Risch at Mila. Then there is a set of solutions from Poggio's lab, and there is a set of solutions from another lab, DiCarlo's lab at MIT. And the 3 have come up with somewhat different solutions, although the DiCarlo solution looks very similar to the Poggio in some extent, not entirely, to improve that. But it's still not completely, no model has been completely trained or tested to show it makes similar mistakes to humans with adversarial attacks. And it's similarly robust to humans against adversarial attacks. There's it kind of raises our bar. So I think for vision, our bar is a little bit higher than it is, for instance, like you were saying, for other domains. And thanks to things that we have found, I think in learning and memory, in my opinion, our bar is higher because of the 20 years of not just reinforcement learning, but also representation learning using reinforcement learning algorithms. That we understand some things about the hippocampus, entorhinal cortex, and prefrontal cortex that we didn't know 40 years ago, for instance. I think these things are they went all very hand in hand. You have Tolman's theory based on a behavior he observed, which went against behaviorism. It said latent learning. Rodents can learn to navigate somewhere without having been sort of reinforced. Therefore, there is a way in which animals can learn without direct reward, without constantly being reinforced on it. Therefore, his conclusion, there has to be a cognitive map. And if you read his books and if you read his papers, he actually connected this to mind in a broader sense. He connected this to the notions of war, to human like cognition in social domains. He was like very broad about it. He wasn't saying this is everything there is to know about the mind. He was actually very clear how much more needs to be done and where this idea could go. And I really appreciate his writing. I think he's one of the best scientific writers, honestly, that I've ever read. Then we come up, because 30 years later, there is the discovery of place cells. 30 years after place cells, there's the discovery of grid cells. 10 years after that, we have all of a sudden reinforcement learning models that explains them. And that's the time where like we have like the Nobel Prize for these things too. So there is a nice kind of interaction between just behavioral observation of an animal, theory, very kind of extensive, expansive mind, not reductionist ideas from of cognitive maps. Then discovery of cells, which is again going down to a level of implementation in the body, and then going back up to algorithmic level, and then making predictions. And all of a sudden it turns out, oh, our models make these predictions. Now let's see which model wins, because we need to run new experiments to see which one holds up, which is like the field where I think I'm like, what is it, 5th generation or something like of this kind of endeavor since Tolman. So there is some ways in which the bar has been raised, for instance, for spatial navigation / memory / vision in different ways with different kinds of mathematical histories. So you're totally right. But then from this bar where we are now, there's so much ground to cover still. We're still at infancy, right, in terms of computational neuroscience. And then what comes next for vision might be closer than it is for memory, hippocampus, navigation. And for some other domains, it might, like prefrontal cortex, we're pretty far from it. Like, are they basis sets? Is this like a linear algebra happening in a dynamical systems latent state? Is this like a pointers? Like, there's all these different theories that have been around. And then we don't have a mathematical model that properly addresses that. But, you know, I think the fact that convolutional neural networks have done well in the past 20 years or 15 years in the domain of vision, you know, they're still not perfect. They still have a lot of way to go. I don't know if I would consider that yet an entire win. I do consider it an intermediate win. And I do agree with you that the bar is now higher for vision than others, but I still think we still have a lot to cover.
But there are just, you know, but there are two lessons, right, Grace, to learn from the vision one. You know, is it glass half empty or glass half full, right? In other words, I remember hearing, you know, Bill Bialek giving a talk, and then David Cicillo gave a similar talk on this notion of universality, right? That, you know, that the final structure that is reached after an algorithm has worked on the problem. So, you know, it's the notion of convergent evolution, right? The wing was convergently evolved on a bat and a bird and even the flippers of other mammals. They converged on a similar asymptotic solution, but they did it in completely different ways, right? So in other words, the fact that the intermediate layers look similar in the neural network and in the macaque brain does not mean that they were reached in the same way, any more than a bat wing was reached in the same way as a bird wing. So are you not confusing the final product with the process that led to it?
Well, there are ways in which a bat wing and a bird wing were reached in the same way, and it's because they're subject to the same physical constraints. And you could say the same thing about neural networks when you say, if you're arguing that you found the right kind of data to train the neural network on, it's like, this is what's physically out there in the world. These are visual inputs that you would experience, and that's partly why you're able to get the right representations.
That structure in the world, that structure, I don't deny about the structure in the world. I agree that the point of universality is the structure of the world or the problem limits what the answer can be to that problem, right? But that's not the same as saying algorithmically it was reached in the same way. In other words, what I'm saying is that it may well be that we see convergent evolution on the how to solve object recognition in the world, but that doesn't mean that it was done in the same way by us and by. Now there are similarities. I understand, you know, this linear, non-linear sort of units, and there is some computational similarity, but I think we have to be careful in general not to say that because the end result converged on a similar solution, that they reached it in a similar way computationally.
I mean, in this case, we know very explicitly they didn't reach in a similar way because one's trained with backprop and the other one is evolution,
but it's more than
development, and all of that.
Sure. I guess it's just the point is what does it ultimately mean when one sees this similarity? What exactly do we think that means?
Mm-hmm. If the neural productivity were perfect, would you then say they're reaching things the same way? If you could predict a real neuron perfectly from the corresponding layer of an artificial neural network?
The algorithm is different, right? Like one is using, I mean, you said yourself, like if the processes that it's using is different, then behaviorally it's doing the same thing. And maybe there is a way to compare representations, but the process would be different because one is using backprop, right?
And it gets to the problem, you know, to your point, you know, we've done experiments where we can look at somebody and they look at endpoint, you know, at their asymptotic behavior. If you looked at the two subjects, they look identical, right? You can't tell. But if you do some sort of test of, I don't know, generalization or some sort of test other than, then suddenly you notice that they're not the same, right? Yeah. And I think that's what Ida's point is. It all looks great until you do an adversarial attack and then they suck, right? So in other words, something is not the same. So you have to be careful about what does the same mean, because you can always find some cruel test that suddenly breaks down the similarity, right?
Yeah, and I think, I mean, there's this standard acknowledgement that no model is perfect. And so obviously you want to capture the similarity in more and more domains, you know, behaviorally, neurally, the better you can fit the real data with the model, presumably the more the model is matching what the real brain is doing. But I do think that sometimes people have a tendency to either demand perfect fit in all domains from the start to even consider it a worthwhile pathway to go down to use these kinds of models, or the goalpost keeps getting moved, or people assume you can't learn anything from the model until it fits in all of the domains that they care about. And so that's just the almost a general point about modeling that I actually tried to kind of implicitly discuss in the book, that they all have their limitations. They're all abstracted away from the real data. They all have caveats, but the question is, can you get to the next interesting step by using the current model?
Right, the models are as good as the next set of hypotheses and experiments that they generate, right? Are they, what's it called? The sort of notion of a useful scientific project versus a dead-end scientific project. And I completely agree that these are leading to very interesting questions. Do we have anyone else, Ida, in the question room?
I think we had Maxted. I don't know if he's still here. I'm going to see if he's still here. It seems like he might not. Oh, he is here. Wow, there's a couple of him.
Oh, invite him in then.
Sources, but we are 5. Let me see. I think I think I invited 2 Javier, so I need to kick out the fake Javier so that you can join. Oh, for some reason, I see. Okay. All right, so now we can add Maxted. All right. And we can wrap up. So hopefully
I don't see Maxted there. Is he in the room, or am I not seeing him?
He was in my list of people that I could invite. Or I can just read his.
He's requested that you read it because.
Oh, it says still here, but ask for me on the bus. Okay, he's on the bus. All right. So Maxted says, "Oh, Nidhi. I invited Nidhi, but she wasn't there." Okay, so she says, "What was your favorite story that you discovered while researching the book that didn't quite make it to the final version?" That was Maxted, actually.
Oh, that's tough. There were a few topic areas that I didn't get into as much as I wanted to. And actually, like grid cells and place cells were one of them. I tried to put all of the good stories in, even if it meant a little bit of shoehorning. I can't, I'm trying to think of. Also, this research was like 2.5 years ago now. So I might not be able to think of a really good story that didn't make it. there's a lot of interesting stuff about Claude Shannon, which obviously he's been written about a lot. But I want to read a biography of him, and I also want to read more about Helmholtz. Those are the two people that I walked away thinking like there's a lot there that I'd like to dig
What was
in.
the name of that machine that that he made, Grace? Where
I think it's the Impossible Machine.
The Impossible Machine, where you switch it on, a hand comes out and it switches itself off.
Yeah. Which that Claude Shannon, yeah, that just sounds so much fun to me.
That's one of the first things, John, that you build in your electronic circuits at universities, like when you study CS. Like that's one of the first things that undergrads make, and everybody feels so cool because you put it in your room and everybody's like, whoa. You ever go back in time?
Yeah. Are you gonna, so Grace, it's such a great book. You obviously have a real gift of synthesis. Are you gonna write another one?
Very good at this.
I took a break from writing for a bit after finishing writing the book. I would like to write another book. I found the process not as terrible as some people warned me it would be. I had a pretty clear game plan going in about how I wanted to organize it and all of that, so that helped. I would definitely want to write another book on something. It's really fun to have an excuse to dive deep into something that isn't your exact research, especially if it lets you go in like the historical direction or the more kind of understanding the social context direction. I like having the excuse to read these obscure papers that I wouldn't otherwise come across at all.
Because one thing you did really well, and I wanted to ask you about, now I'm remembering, is you managed to always open with something that seemed to be a little bit unrelated, and then you tied it in really well. Was that deliberate, that you said, I'm going to give you a segue in, it may not seem obvious, and then I'm going to link them? I mean, it was something you did over and over again really well. Was that intentional?
Yeah, I think that is a writing style that I like to use, especially for topics related to mathematics, because one, I think, especially thinking about this for a general audience, like people get scared if think that they're just reading about mathematics, like they don't just want to see mathematics directly. And so by introducing a concept that like you don't realize is going to tie into some of the mathematics or computations that come later, it's just like a more gentle way in. But also it's pretty easy to do that with mathematical topics because mathematics is like where analogies live. It's like the same equation describes this and this. So if I want to talk about this later, I can describe this more familiar thing to you now, and then be like, oh yeah, but that's the same as what's going on here. And we know because we use the same equation to study both. So I think, yeah, for writing on mathematics, that kind of switch of the topics after you've introduced something works pretty well.
And Grace, we have like a follow-up from John that I didn't see. And he says, seems unlikely that animal brains such as rat brains are highly symbolic and our brains have virtually identical architectures to rats. Well, or am I thinking about this wrong? So that's one thing that he asks. And finally, Mario asks, how long did it take to write the book? So maybe those two can be our last questions.
Yeah.
Okay. I can answer the second one quickly. It took like 1.5 to 2 years from really finalizing the proposal to when the book was due.
And how long did the proposal take?
The proposal wasn't too bad. It was kind of this step-by-step process where I knew people who wrote for this publisher, and I met with the editor to talk about like broad ideas that they would be interested in. And then I went and wrote a proposal, and that took like a few weeks to get together to decide on the table of contents, and you write a sample chapter and stuff like that. And then I submitted that, and then you sign the contract that tells you when you need to be done by. So that's, without that contractually obligated end date, I think it would have taken longer. But I tried to keep on a set schedule, knowing that was looming about, 17 months from when I signed the contract or something like that. And then if you guys want to discuss whether rat brains are the same as human brains.
One thing that I did want to mention, Nidhi, which is a very simple question. She says, is there a record of communication between Fukushima and Hubble and Weasel?
I didn't come across anything direct between them. The neocognitron version that I showed didn't get published until like 1980, so it was actually a while after Hubble and Weasel were doing that primary work. So I don't know that they ever had direct communication. Maybe since then, because like Fukushima became famous for it and all of that, maybe they've met up at some conference.
You do mention in your book Grace, where I'm blanking now on the person that Human and Weasel don't mention in their Nobel Prize speech.
Human Weasel don't mention Selfridge, is that? Or
Selfridge complained.
That they didn't mention Letvin, maybe.
Yes, Letvin. You know, what does the frog's eye tell the frog's brain?
Yeah, which was kind of, laying the groundwork for this kind of hierarchical concept of how the visual system works.
I actually really enjoyed reading those parts, and I think you're a fantastic storyteller as well as a scientist, because I think the way that you wrote, it was incredible. Like, I was like, wow, this is like a very clear but narrative way to say something that's computational in a way that's engaging and easy to read. I love it, and that's why it's on my Kindle, because it's a perfect subway read in New York. And it's like, put it in your pocket and pull it out. It's fantastic. Thank you so much for joining us. Thanks for sharing. Thanks for staying this long. And this has been really great. And, hopefully we will get you to join other sessions as a participant and ask others your questions too. As you see, like Melanie and others, like we have a lot of alumni who join.
So how many, and you know what we want, Grace, is, there are 3,000 members of the Salon, and let's hope they all buy your book.
That would be lovely.
They should. and honestly, it's a really one of a kind, and everyone should read it.
It's pretty unique. I was reading and I was like, should I translate this to Farsi? I was like, I don't have time. Should I tell someone to translate it to Farsi? I think it's a very well written book and an introduction to the topic that will engage people. I apologize for New York sounds. Okay, sorry, I closed the window.
Have you gotten? I mean, we keep saying it's the last question. What sort of feedback have you had? Has anyone sort of, made any objection to it, or have you basically? Have scientists in the field sort of had a problem with a particular take you had on a particular topic? Were you corrected? How, or has it just all been praise?
It's not all been praise, but there are some just errors, typographical and otherwise, that people have told me about, which I appreciate, because there will be a paperback print.
Yeah, there was an error in your Bayesian equation.
I know that's a big one. People told me it was clear from context that this was an error and it didn't confuse them and stuff. But yeah, that's very frustrating. So I'm going to fix that. So people have told me about those kind of small errors. I haven't been told about any like that anyone's upset about any major conceptual claims that I'm making. More like the criticism that I've seen in terms of book reviews and stuff is sometimes in the direction of the mind isn't the brain, or we can't use computers to understand the brain. Just kind of a fundamental disagreement with the premise that we could use computation or mathematical methods to understand the brain on some level. And then another class is more in the direction of why isn't this a textbook? This wasn't as detailed. I didn't learn how to implement these models from reading this or something like that. So that's just kind of a class error of this wasn't the book that they thought it was.
Yeah, that kind of person would need to have their head examined, it seems to me.
I have actually, my experience being someone who does popular science writing as a practicing scientist, I have encountered scientists who I think just don't know that the genre of popular science exists. It's either it's technical science writing or it's a novel, and I don't know what this in-between thing is. So that happens sometimes. But to the people who are familiar with popular science, they've mostly been positive about it. It's a certain type of person who's going to pick up this book, given what it's about. But yeah, I think people have been mostly positive.
I don't read all the books that come out about neuroscience, and there's a lot of them in popular science. And I personally thought that this was a very well-written book. I was very pleased to have spend the time. It felt very good. And I just want to say also, John, it's possible that some of us might have scanned and examined the brains of the people who have said those things.
Well, listen, Grace, honestly, thanks for being such a good sport and answering the questions, and congratulations again. Awesome.
Thank you. Thank you for having me. I'm not good at accepting compliments about the book, but I appreciate that your compliments have been in the direction of exactly what I was trying to do with it. So that makes me feel good that I achieved the goals that I set out to do.
Yeah, well, we also criticize it a little bit. It's not all.
yeah, that I can handle. That's more comfortable.
No, but I mean, look, you know me, I'm sort of a critical person, but I'm also a book snob. I love books.
Yeah.
And I think, honestly, as a book and what you did and how you synthesized and wrote, it's a success as a book. And that is not easy to pull off.
No.
And you should be, and that is just a fact. And anyone who says otherwise will just send them to us.
We'll examine their head.
All right. Okay. Ciao.
Bye, everyone.
Bye.
See you next time.
Bye.